Good morning, everybody, and thanks for inviting me to present the status of what was called the Mediterranean neutrino telescopes, ANTARES and KM3NeT. I'm Ronald. Now, let's see. So first, a little bit about my talk. So this is sort of the landscape, as I see it, of neutrino astrophysics. Very simple, two-dimensional. Along the x-axis, we have the energy scale. On the right, you have the high energies, TeV to PeV. On the left side, we have the low energies, GeV scales, and even down to MEVs. Now, the other axis, which is sort of an invention of mine, is sort of the astroparticle axis. On the bottom, oh, the wrong button, right, here we go. So on the bottom, sort of have more the astronomy type of subjects. And on the top, we have more the particle physics type of subjects. And what I've drawn in this landscape are the subjects covered by the telescopes I'll be talking about. And these are the KM3NeT ARCA, ANTARES, and the KM3NeT ORCA. For example, the top you have the neutrino mass hierarchy. Here you have neutrino point sources. So my talk will sort of cover this, and I will introduce these telescopes in a bit. So I apologize for breaking the symmetry to this side. So now, just a quick reminder, you may know this already. So large volume neutrino telescopes aim to detect the terrain of light of the charged products of neutrino interactions by instrumenting large volumes of water with photomultiplier tubes. You have some schematics. In general, there are two types of events. So which we call track events, so which are basically muons from charge current mu-neutrino interactions moving through the water, emitting terrain of light, which you can detect with your array of photomultipliers. Cosmic ray muons also tend to look like this. And then you have more compact energy depositions, typically from electrons from charge current electron-neutrino interactions, hadronic showers from the neutral current interactions or the hadronic part of a charge current interaction. These tend to be a bit more compact. So you see a little schematic, left the track, right shower, and this is sort of at 2.5 to 3.5 kilometers deep, because these are the typical depths of the ANTARES and KM3NeT detectors. Right, so I realized this is the first time I have to talk about ANTARES in the past tense. So I should actually say ANTARES was a neutrino detector, which essentially consisted of 12 vertical lines with sort of 25 stories. And each of these stories had, say, 3 10-inch photomultiplier tubes encased in a glass sphere of 17-inch. So these are the detecting elements. So with this, you can we instrumented 10 megatons of volume, 2.5 kilometers deep outside of the shore of Toulon. So what you see on the top right here is the deployment of the first line. So you see the 25 stories on deck. It was Valentine's Day, so somebody drew a little heart on here. Went in, and now May of this year, we actually recovered the last line. You see the line being dragged behind the boat here, because of course these spheres, they float. So it operated for about 16 years. Now, as sort of a successor to this, we have KM3NeT, which we call a multi-site deep sea neutrino telescope. It's multi-site because we actually built 2 detectors for now. We have ORCA outside of the coast of Toulon. We'll do oscillations research, neutrino oscillations research with cosmics in the abyss. That's sort of the acronym ORCA. And we have ARCA outside of the coast of Sicily, which will do more astroparticle research with cosmics in the abyss. Right. And we're also part of a network for sea and earth sciences. We're on the S3 roadmap. We are a single collaboration for these both these detectors. We use exactly the same technology for both detectors. Only the scale is a bit different. We're mostly a European collaboration, but we also have got collaborators in Africa and in Australia. So let's see. The technology used in KM3NeT is a bit different than in ANTARES. It's sort of an evolution of this. So instead of one 10-inch photomultiplier tube in a 17-inch sphere, we put 31 smaller 3-inch PMTs in the same sphere. Actually, you get the same amount of photocathode area as 3 10-inch photomultiplier tubes, but on top of that, you can do better photon counting You have directionality, and it's a lot cheaper to do it like this. So 18 of these spheres, you can put them on the line, on a vertical line, which we call a detection unit. Now the distance between these lines, it varies. Between the DOMs in the line varies between ORCA and ARCA. In ORCA, you put them closer to each other. You also put the lines closer to each other. And if you take 115 of these detection units, you have a block. And one block of ORCA, which is actually the full ORCA we aim for, is about 7 megatons at 2.5 kilometers deep. ARCA will consist out of 2 of these blocks, this 115 detection units. Things are spaced a lot bigger. So for example, 38 meters vertically between the DOMs, which we call these spheres. In the end, 100 meters between the lines. In the end, you instrument about 1 gigaton, so 1 cubic kilometer with 2 of these. And it's actually a bit deeper, 3.5 kilometers. Besides that, we need a lot of infrastructure. We need cables on the floor for optical transmission of our data. We need to get power there. We actually transfer all photons we record to shore via the optical connection. And that's where we do the filtering, the triggering, and the reconstruction. We call this all data to shore. Now, sort of the status, we are in the midst of constructing this detector. So this map more or less shows all the institutes contributing to the actual building of the detector. So we have to build these spheres, we have to put them on lines, we have to deploy them, we have to prepare electronics, which is quite a logistic challenge sometimes, but we're doing quite well with this. Actually, last month, we deployed 11 detection units in one expedition, actually 2 sorties of the boat, but we deployed 11 detection units for ARCA, so the deep and big side, so that we now have 19 of these detection units operational, which is, I think, a significant step. For ORCA, so the compact detector near France, we currently have 10 DUs operational, 10 of these lines, after sort of dynamic recent history where we had to recover some of these lines. But that's under control. Actually, after summer, we'll continue with deployments. Both sides will be deploying about 4 detection units, maybe even more. For the remainder of the talk, if I, for example, say ORCA 6, I mean ORCA operated with 6 detection units, with 6 lines, and the same goes for ARCA. So this number indicates how many of these long lines are in the configuration. Yeah, so I could run a PowerPoint, so I can show a moving plot. So these are 2 event displays, actually a few event displays. On the left, this is data ARCA 6, downgoing event, so likely an atmospheric muon. On the right, well, now I mess up here. Yeah, on the right we have, oh, okay. You see, you should not try to put animations in your talk, right? Okay, well, you can look this up in an upgoing neutrino, an upgoing event on the right plot. So that's likely a muon from a charge current in muon-neutrino interaction. So, very nice. This is real data. Data, not, yeah. I don't like the word real data as data, right? So, you can have simulated data, but this is real. A few event displays. So what's also moving is this plot on the top left. These are the lines swaying in the water, because water makes our detector move. In order to do our physics, we need to know the position of all of our DOMs to 10 centimeter accuracy. Actually, it's about the PMTs, we need to know them to 10 centimeters accurately. To do this, we have acoustic beacons on the seabed, and each of these DOMs has an acoustic receiver. So with trilateration, we can determine the position of these DOMs and do some constraint fits on using this line mechanics. And actually, we achieve this 10 centimeter precision. So you can see this on this plot here on the bottom right. So what we do, we check with reconstructed events how much we have to move a line to get a better likelihood or a better fit. In 2 cases, blue is just having a static detector which does not move, which we do not correct for the actual movement. And the blue one, and the orange one is actually using this active, this calibration, this active, this continuous alignment. And you see the width of this distribution is 5 centimeters and centered around 0. So that's exactly what we want. So we're very happy with that. So we know where our detector is. But you also need to have absolute pointing. So you need to know where your detector is looking at, right? So we don't have a standard candle source on the sky where we can point at. So actually we use an anti-source. We use the sun and the moon, or at least the shadow they cast in terms of cosmic rays, right? So they block cosmic rays. And thus we see less atmospheric muons coming from the direction of the sun and the moon. So we can use this. Actually, we can confirm with 6 sigma that the sun is there. We're not quite sure if the moon is there yet because we only have 4 sigma. So we'll tell you later. Right, so we see the sun and the moon. So on the top left, you see actually a picture of the sun as seen by, or anti-seen by Orca. So now for the talk, so I will be talking in the beginning about the bottom right part, so sort of higher energies, and I'll be focusing on ANTARES and KM3NeT, so more the astronomy corner. Right, so we're building, and KM3NeT is now as big as ANTARES was, essentially. So in terms of effective area, so blue is ANTARES, and the other 2 curves are ARCA and ORCA together. This plot has been made for ARCA 6 and ORCA and ARCA 6 configuration. So by now they have grown significantly. The thing is, obviously, that ANTARES had been on for a long time, so we got 40 times more lifetime. Now, in the final configuration, we see a comparison of the sizes. So this blue is ANTARES, and this is ARCA 1 block. So this is the effective volume as function of neutrino energy. So this was the effective area as function of neutrino energy. So you see, so they are significantly larger than ANTARES when finished. So when you have a telescope, you need to know what your pointing is. Here for ARCA, we have the angular resolution, so the accuracy which we can determine the direction of a incoming neutrino, or rather the resulting lepton, right? For ARCA, we achieve way beyond 0.1 degree at the highest energy, right? So this is the energy axis, this is the angular resolution in degrees. So here's sort of 10 to the 7, here's 10 to the 6th electron volt, or GeV, actually, sorry. And on the bottom, we have the resolution for cascades, which are typically a bit harder to reconstruct in terms of direction, but we achieve sub-degree resolution on that direction. So together, so the size and these performances, we should be able to confirm the diffuse neutrino flux as measured by IceCube within 1 year of data in case of a full detector. So that's this blue line is this flux, and these are the sensitivities. It's function of observation years, right? So now about measurements. So ANTARES obviously did a few measurements. This is not with the full data set as we have it now, but it's the latest analysis on this. So this is the diffuse cosmic neutrino flux. Now it's not significant. We didn't discover the flux, but it's sort of confirms it's consistent with the measurement from IceCube. So we did search for diffuse neutrino flux from both tracks and showers. Black points of the data, the energy right here. So it's sort of consistent with what we measured, and that's good. One target we've looked at in a few analyses is the galactic plane, because you expect neutrinos from interaction of cosmic rays with the matter there. In particular, we have looked at this Krag-Gamma model. We've used the full morphology and spectrum of this model. It did analyze both with tracks and cascades. We set the limit, so we didn't do discovery there. We also combined together with IceCube to set an even stricter limit. So you can see these in this plot here. The green ones are the ANTARES only limits, and the blue ones are the combined IceCube ANTARES limits. We also did an attempt with the ARCA 6, but obviously we did not see anything because the detector is just way too small and didn't live long enough yet. Right, so of course you want to see point sources of neutrinos. We did several studies over the years. This is, for example, we did a full sky search. This is the most recent one. No discoveries here, so nothing significant, but we do have 2 most significant in our data set points in the sky. The reason we mention them, because these objects, where they're close to, tend to pop up in other analyses too, and they're actually close to, both are close to high energy IceCube events, right? So So one here, close to J0242 plus a number, and here another one close to MG3 here, both blazars. Catalog searches, obviously we do also do catalog searches. Right here on the right plot, you see the limits we set on a set of objects from this catalogs. Nothing, no discovery, but the most significant source is actually the one which also shows up right here. And you see the significance of nothing to write home about, but nice that these things pop up all the time. So we did the same thing also with a limited set of ARCA data, and of course we didn't see anything spectacular, but it seems to work. So we're looking forward, because this plot also shows the sensitivities for full ARCA after 3 and 7 years and compared to the ice cube sensitivity right here. So very promising. Blazars seem to be very hip, so we also triggered by this ice cube data correlation with this blazars and VLBI data. We took that set of data and we did a 2-point correlation function here. No discovery, but we do see hints for subdegree angular clustering right here. So this is about 2.3 sigma, right? So this is the different distance between the events, and you see the amount of correlations. We also did a time-dependent search, so basically looking for flaring. So you have this moving bin in time, so you can see if you have a flaring object. These are the significances we found for this this particular set of objects. We had a few above 3 sigma pre-trial. But you tend to see the same names popping up. So J0242. This one is J1500, and then another number is very interesting because it also showed overlapping radio and gamma flaring here. So now, oh wait a minute. Okay, right. So we had a very elaborate multi-messenger program with ANTARES. So we provided triggers to experiments, we received triggers, did follow-ups, we were in these networks. We had, for example, our own optical follow-ups. We had on and offline analyses. I'm not showing them today. But this is passed on to KM3NeT. So, for example, KM3NeT Orca had its first ATEL follow-up, I think, a few months ago for this blazar here, which was in the coincident ice cube and Baikal. So it's we hope to set up this program again. So one of the subjects, of course, is gravitational wave follow-up. We did this for ANTARES for 2 run at least. We also did this for KM3NeT. So basically what you do, you get you have a trigger, and you, in time and in space around that moment, you start looking for an excess. We typically do this with the on-off method, right? So you compare you estimate your background from off regions away from the region of interest. So nothing in particular found. What we did, we set upper limits on the total neutrino flux energy emitted in neutrinos from these objects. So it seems to work. So this was done with Orca 4 and 6 data, so very small detectors, right? Like I said, I already shown this slide. Now the thing is, right, so because this is a Cosmic Ray conference, I should mention this. So what you see here is the incoming direction of track, muon track events. Obviously on the right side, these are the downgoing ones, right? So this is upgoing, coming to the Earth, this downgoing. So this is the region, this left is for ARCA, right is for Orca. So here you expect atmospheric muons in this region. So we've always had this discrepancy, right? So we could not accurately simulate, right? The data Monte Carlo did not match. So in this case now we have an excess when you go straight down, and we go more shallow, we see less than we predict in both ARCA and Orca. So we're now actually trying to do physics with this. I'm not going to give the details, but if you want, you can talk to me afterwards. But this is a very exciting field too, and we hope to contribute in this in this respect. Now, we do many more topics. We do dark matter searches, look at all kinds of objects, gamma ray bridge. Angela gave a talk last Monday, starburst galaxies, monopole nuclei, and other exotics. We do combination with gamma ray observatories. It's a wide program. Now, I'm going to move to the top left part of this plot. So we're going to look at lower energies, and we'll be focusing more on the ORCA detector, and a little bit ANTARES detector. The thing is, supernova neutrinos are there, but you actually also do them with ORCA, so it's plot is not very accurate. So the way you do neutrino oscillation physics, which is sort of the main subject of the ORCA detector, is by looking at atmospheric neutrinos, so created in the atmosphere from cosmic ray interactions, passing through the Earth, and you measure their incoming direction, angle, and type, right? Or at least whether it creates a shower or a track. Different distances, if a neutrino travels different distances, so they have different lengths on which they can oscillate. In the case of neutrino mass hierarchy, you also see a different amount of matter in the Earth. So this is typically what you do. So ANTARES did some sort of, we would call it proof of principle studies on neutrino oscillations. So, for example, you see here the reconstructed energy over the incoming angle, so E over L, essentially, sort of proxy for E over L, which the oscillation probability depends on. And you compare it to what you expect in case of no oscillations, which is the red. In the case of oscillations, blue, and blue, and in case of your own fit, depending on the neutrino oscillation parameter. So in this way, you can measure neutrino oscillation parameters. This was done by ANTARES, was sine squared theta 2, 3, and delta m squared 3, 2. So sort of the atmospheric oscillation parameters. Not very competitive, this black line, but at least we knew we could do this. So the program in ORCA is quite extensive. So we want to measure atmospheric mixing parameters. We want to measure, in particular, neutrino mass ordering. And we want to look at new physics, stereo neutrinos, decays, non-standard interactions. So this analysis, right, this the oscillation parameters we've done with the small ORCA detector. So it's basically 6 lines and 1 year of data. So it's about 1 kiloton year, which is actually quite small. You see the result here. So this is the ratio to the no oscillation hypothesis, and this is L over E, the length traveled by the neutrino over the energy which you reconstruct. Blue is no oscillations, black is the data, and then we have the prediction from the world best fit parameters, new fit 5, and the actual fit we do in light blue. In this way, you can actually, again, determine these atmospheric oscillation parameters, sine squared 2 theta and delta m squared 3, 1, and it looks a lot better than the ones measured by ANTARES, because the energy threshold is lower, more in the region of the neutrinos, which more in the region where you actually see significant effects of these oscillations. So this is for, again, a small detector, so 1 year of data. Now, when ORCA is finished, this will be quite a lot better, actually very much better. So this is the prediction of the accuracy with which we can determine these two oscillation parameters. So this is this red line here, and again, also compared to current measurements, as was in the case in this plot. So very exciting. Now, the main the main physics subject we want to tackle with ORCA is the neutrino mass hierarchy, right? So there are 3 mass eigenstates of neutrinos. We know the mass square differences between them, but we only know, we don't know the sign of the of one of these differences. So is this third mass eigenstate lighter or heavier than these other 2, right? Now, the oscillation, so the Earth consists of electrons, so electron neutrinos are more affected when they pass, they have an extra interaction channels when they pass through Earth. So they experience an extra potential, so it means that you modify the oscillation probabilities when they move to the Earth. And actually that depends on the neutrino mass ordering. You predict a different oscillation pattern when this mass eigenstate is lighter or when it's heavier. So this is one way to determine this neutrino mass ordering. Here you see our sensitivity. This is the expressed in sigma. So the the significant which you can exclude the other hypothesis in case of normal ordering in red and inverted ordering in blue. Right. So one parameter which is not constrained very well is this theta 2,3. So that's why we typically plot it as function of this theta 2,3 for 3 years of data here. So in case in normal ordering, and we're sort of on the right of the plot, we can do in 3 years, we can get 3 sigma. And here you see for a fixed angle, 48 degrees for theta 2,3, you see the significance as function of the integrated measurement time, basically. So you get 3 sigma after 3 years in case of normal ordering, which sort of tends to be the corner where this where these parameters should be. Right, very promising. Like I said, we also do very low energy neutrinos. These neutrinos, MEV neutrinos from supernovae, you can't detect them individually. You cannot see them. They just don't produce enough light. But if you have a flux of these neutrinos, antineutrinos, and that form inverse beta decay, you get an enhancement of your count rate in your whole volume, so that you light up your whole detector. With higher count rates, you also get higher probabilities of coincidences of hits on the same DOM, so that multiple PMTs are hit sort of at the same time. Now, and you do this for the whole detector, right? So what you see here is the amount of PMTs hit at the same time, so we call the multiplicity, and here's sort of the rate, and we compare that to the background which you have, because you have potassium-40 in the water, you have bioluminescence, you have light all the time. You see that around a multiplicity of 6, you can exceed it for large progenitors, right? In this way, we can sort of see supernovae until the edge of the Milky Way, and the more heavier the progenitor is, the more significant you can see that. So the sensitivity here in sigma, and here the distance in kiloparsecs. We are in these networks to do this. Other topics, and I'm almost finished. We do indirect detection of dark matter. We prepare combined analysis with other experiments like Juno. We can actually significantly enhance our sensitivity to the neutrino mass ordering when we do this. We sort of are in completely complementary spaces compared to Juno. So we are very, very promising. We constrain the tau neutrino flux, can do non-standard interactions, sterile neutrinos, Earth tomography in composition. We can measure the Earth composition with neutrinos. And we're a node in the Sea Science network. There's actually a little robot which is on the bottom doing some research. It's connected to our detector right here. This is a seismometer right there. Before last slide, some impressions of building a detector. Here you build the DOMs. Actually, this one NICAF in Amsterdam, put together on a cable. Then you put them on this deployment device, and you really should look up the YouTube movies of these deployments. It's really spectacular how this one unrolls for 700 meters in the water. It's really nice. You hoist it down to the bottom, view a little bit on the water, and this is sort of a junction box. So this is where we connect all these lines to. This one is still on shore here, but this is an underwater robot, plugs it in to your line and to this junction box, and then a cable goes to shore. Really spectacular. You can do this at 3.5 kilometers depth. So as a summary, so after 6 years, ANTARES has come to an end, leaving a great legacy. And KM3NeT is an excellent successor. The construction is now well underway. We have first promising oscillation results, and we are already doing some interesting pilot